Hello DC Circuit students. In this series of videos we are going to look at calculating, simulating, and then measuring equivalent resistance and node voltage for a series parallel combination of resistors. So we're going to start with the calculation part, and I'm going to start by drawing out the schematic on my whiteboard. And I'll just have to start with a note that the values of resistors that I'm showing I have already measured with my ohm meter. So these are a little bit different than the standard nominal voltages because I've already put in, or I've already confirmed what their actuals are. So we have our source, and we have a resistor coming right there in series with the battery, 976 ohms. A 3.89K, which would be a nominal 3.9K. 2.69K, which would be nominal 2.7 if you were going by the color code. And of course these values are well within the 5 or 10% tolerance cited for each resistor. Since I confirmed the actual resistance of my resistors, just in case I didn't see a color band correctly, this allows me to put in the actuals in my calculations, so my calculated values and my as measured values are a little bit closer. So we've got a branch, 3 branches in parallel. And then all of this is in series with another resistor. So we'll just call this V source. It's a battery or other DC source with a positive, so we're going to have current flowing, source current, conventional current flowing in this direction. And I am going to assign a ground, which is a 0 voltage point. And this is very important when we're trying to correlate our calculations with our circuit simulator and what we're measuring with our voltmeter when we start measuring from the proto board. But it's especially important since we're using a simulator because it requires a ground or a 0 voltage reference point from which to calculate everything. So it won't use a floating. It says, hey, where is 0 volts? And then it's going to use Ohm's law, and it's going to use addition of voltage from a source to go up or down from there. Okay, so we're going to start by using some just series parallel combination rules and go ahead and simplify this circuit a little bit. And I'm going to keep kind of scaling down so I can keep showing it. It's going to get a little bit smaller each time. So let's start by simplifying within the parallel branches a little bit. And I'm just going to redraw the circuit each time to show the steps. It's good practice here. So I'm not going to do anything with that first resistor. It's just going to sit there. But I'm going to go ahead and combine the series resistors in each of the branches. So I have 3,890 and 2,690. And I'm just going to go ahead and add these with my calculator just to make sure. 3890 2690 plus, I'm not using the ohm symbol because it's pretty much understood that these are all resistance values. That's something you'll see sometimes on an interim calculation in some textbooks or articles. It's pretty much assumed that you know that the resistors are in ohms. We don't necessarily need that straight there. Looks a little artificial. So, as long as we don't draw loopy wires that make it look like an inductor. So on our next branch we have 2,150 ohms, followed by 5,560. So we have a 7,710 ohm branch, and then the last one just has a single resistor, 8,160. So that was our first simplification step. $1,140. Okay, next we need to collapse that parallel combo down and get a single resistor that is equivalent to that parallel combo and show how it fits in. So we're going to keep the 976. Now I'm going to go ahead and I'm going to just use my calculator to apply the parallel resistor combination. So 6,580 inverse, 7,710 inverse, 8,160 inverse, add, invert the total, and I get 2,474, rounded off to whole numbers. So as a first check, is this less than the lowest of any of these? Yes. So I'm not going to do any more checking than that, but that's always a good, easy initial check to see if you've done a parallel combo correctly. The combo should always be less than the lowest resistor that you have. Almost there. Series combo. Okay, so we'll do a little equivalent here. So now all we have to do is add these numbers up, and we should end up with an equivalent plus so 976, 2,474 plus and 8,160 plus. Oops, there's an error. This 800, I was looking at the wrong resistor. This 8,160 has already been included. What I meant to do, this is the final resistor that's in series. Sometimes you have to do a head check. So we have 976 in series with the parallel combo, in series with this final resistor. So 2,140, 2,474 plus 976 plus. So if I were to draw a final equivalent circuit, I should have about 5,590 ohms with our source voltage. So this is our parallel series equivalent. So as it turns out, those kind of little mistakes are very, very easy to make when you're doing calculations, especially if you're going a little bit too fast. So one of the nice things about building a circuit on your proto board is you have a chance to actually do a physical build that is capable of catching the mistakes in your calculations, and vice versa. Your calculations are not subject to the errors of, oh, you didn't maybe put a resistor in the right hole on your proto board, or maybe your wiring isn't quite what you saw. You inherently don't make the same mistakes with each one. You can make calculation errors and you can make prototype build errors, but they're different. And the chances that you're going to make the exact same error with both is very low. So that's why doing a calculate then a build measure eliminates some of the errors, or at least shows you that if you don't get the same result with both methods, there's something going wrong somewhere. So it tells you that you need to do a double check. When you throw a simulation in on top of that, that's kind of in between. You're still doing a build, albeit virtual. Then the program basically goes through the same calculations that we just did, plus applies Ohm's law using calculated currents to get all of the node voltages and the voltage drops over all of your resistors, and so you have an additional level of check. So we've now done the first step in the calculate it, simulate it, build it, measure it, compare. So 5 steps: calculate it, simulate it, build it, measure it, then compare. And we should find out that we basically get the same result with all of them. I am not going to go through the Ohm's law calculations, calculate all of the branch currents and node voltages. We'll just compare the simulator with the circuit build, but we will compare the equivalent resistance for all of them together, or at least the voltage, the expected current flow with the voltage drop, given the source that we're going to use in the case of the simulator and the build. So we will confirm with our simulator and our circuit build that our equivalent resistance should have been around 5,590 ohms. So we'll see how that tallies up. So I will be pausing this recording and then coming back. First, you'll see me back with a simulator of this same circuit, and we'll see what the simulator calculates, and then we'll go to a video of the circuit build and some measurements. Okay, welcome back to our series parallel circuit, DC circuit, calculate, measure, calculate, simulate, build, measure, compare. So earlier in this video we calculated an equivalent resistance for this series parallel network of about 5,590 ohms. So now we're going to confirm node voltages for a given source voltage that we will apply with our physical build, and look at what our predicted voltages are at different points that we can confirm with measurements. And then we can also look at current and voltage and compare and get an equivalent resistance. So this is our circuit build with an open source simulator called Tina. It's Texas Instruments free downloadable simulator. So we have a voltage source here, which you can double click on, and you can see I've set it to 9.28 volts, which is what my battery source will give for my circuit build. And then each of the resistors, you can go ahead and set the actual resistance in ohms. You can also click on tolerance, and you can even adjust things like temperature and whatnot if you want to include the effect of a circuit running a little hot, which you shouldn't. Your circuit should not run hot, but you can simulate all of that. We are assuming everything is running at nominal 25 degrees C. I guess we'll be doing that with a proto board. So we have the same circuit basically. We can use meters. We can actually use an ohm meter to measure an equivalent resistance. If we were to do that, we would want to basically disconnect our network because we don't want a second voltage source if we're gonna use our ohm meter, because it becomes the voltage source. So we can go ahead and connect our ohm meter. And then in order to get the ohm meter to actually run, we will do a table of DC results. And it will be very unhappy because we have a lot of things that we haven't basically take out other voltages, take out node voltages, and take out currents. So now we're only applying ZM1 is the name of the meter basically in the analysis, and it says, aha, this ohm meter is measuring 5.59 kiloohms, which is more or less what we predicted with our calculations. So that's good news that we've got that. We did our calculations right. So we caught our mistake that I showed earlier in the video. Okay, so now I'm going to disconnect the virtual ohm meter, and I'm going to reapply the wires to the voltage source and the ground, which is the point of 0 voltage in the circuit, just like it would be in an Ohm's law calculation. And as you see, as we connect things, you see these little circles appear. These are points where the program is acknowledging that there is an electrical connection. There's continuity there. So it's saying basically that this resistor, this wire, and this wire are all connected together. When you see the little X on either side of a component, it's implied that it's connected, but when you see the little circle, you know you've actually drawn the connection the way you think. These are what are known as voltage nodes. And those are particular points where the program will apply Ohm's law and calculate the voltage versus this 0 point, this 0 ground point. So we're going to redo the DC analysis, get our little table that tells us anything we might possibly want to know. So if you look at the whole table, we haven't labeled everything, but it calculates currents between each one of the node points. It calculates voltages across different components, and then it calculates voltages at each of these nodes, and these are the square labels. And these are the points that we're going to compare to what we build on our proto board. So I'm actually going to get rid of the currents and outputs and other voltages and just keep up the node voltages. And jot these down on, I'm drawing a little schematic over on a notepad so I don't have to keep this up in front of me, or if I'm not working right in front of my computer. So we can start with, and this is something we'll do when we build on the proto board, node 1 represents before we have dropped any voltage over any resistor, so this should represent the source voltage under load. So I'll be using a battery, and I built this circuit on my proto board before, and I measured the source voltage under load, and I got 9.28, which is why I'm applying that in my simulation, and I'm including the as measured values of the resistors, so I should get node voltages that are pretty close to what I measure. So that's why node 1 is actually the source voltage. So if we look at node 2, that's the sort of the second to the last voltage point right before the final resistor, and not surprisingly it should be the closest to 0 of all of these in our table. So we see that the TINA predicts that will be at 3.65 volts. And if we look at the voltage coming out of the source and minus what we drop over this initial series resistor, that's node 3. So that should be the highest right below the source voltage. So you can see Tina thinks that that's going to be 7.66. Then we've got different node voltages in the middle of the branches. So in the middle of the branch that contains the nominal 3900 and the nominal 2600, we've got 5.23 volts. And then in the middle of the second branch we have 6.52 volts. Now something to remember, the order, even though the order in which we place these two resistors doesn't impact their equivalent resistance. It's a series resistor within the branch, and so we would just combine them. But if we're looking for node voltage versus ground, putting this one in this place or vice versa will change the value of that node voltage, simply because coming from this point you would have a different voltage drop over one than the other. So it's important to remember when you build it on your proto board, don't get them mixed up, or you might measure something other than what you expected, or just know that if you want a different voltage you would switch them. Okay, so we have our node voltages. We're going to go ahead and exit out of Tina. I'm going to pause the video again, and then I'm going to come back to you with the video camera, and I'm going to show you how I built the circuit on my proto board, and then I'm going to step through the same voltage measurements that Tina did with my own multimeter and see how they compare. Okay, we are back for the final portion of our calculate, simulate, build, measure, compare. So I have done the build part already, but we'll step you through. So this is what the circuit that we just saw on calculations in Tina looks like built on the proto board, and this is without any clipping of resistors. If you wanted to make this neat, you would have clipped the leads and placed these flush on the board, and it would be very durable. This way it's easier to put it together and take it apart. But we would include, this would be effectively the positive coming from the battery, so conventional current would flow in, would come over onto this row. Here's our nominal 1K resistor, the 976, and then as you can see, row 60 is the triple branch, and over on this side we have our nominal 8.2K, we have our first of two and our second of two, and then the 2200 final series resistor, and then over to the battery negative, which would be ground. So the first thing that I'm going to do is see if my equivalent resistance of my as-built circuit matches my predicted equivalent resistance on both Tina and from my calculations, because it's very easy to get something connected in the wrong hole. But if I get the same equivalent resistance, there's a good chance that I've assembled it correctly, and then my node voltages would be correct. So this is a real simple way of making sure I built it right. So remember, so I try to display my value here. You can see I have 5.9K, which is exactly what I calculated and simulated. So that's a good start to the measurement day. Okay, so the next step is to go ahead and energize it, and I will note that this is a fairly high resistance circuit, so I don't have to worry about exceeding the power limitations of any of these resistors. That's not going to be a problem. So we've got a lot of high value resistors that keeps the current low and doesn't draw down our source too much. Okay. But that said, now it's energized. There's current flowing through the circuit. We don't have any indicator lights, so we can't see it, but we can go ahead and measure the current that's flowing. Now, it's really bad practice to clip your measurement leads to things. So one handy way of solving that problem is to give yourself, take advantage of the fact that there's a lot of holes that are all continuous. So I placed some easy measurement leads there to just help me measure things, and I'll take them away. So now I'm measuring this whole circuit voltage, and I will try to display it. So I have 9.7 volts. So see, I've been plugging in this circuit for a while, so we have actually drawn the electrochemical source down a little bit. It was 9.8, now it's 9.7, so our numbers will be a little bit more off than they would have. Oh, I need one of these back. So now I'm going to basically step through my circuit, and I'm going to place a measurement lead at ground. So we can see this is the ground end of the circuit. It's coming into the battery, which is attached to the negative lead. So this would be the equivalent of my 0 voltage point. So I'm going to basically make it that by saying, okay, everything I am going to measure is going to be measured reference to that point in the circuit, which is exactly what Tina did. So now I'm going to use a nice single strand wire to start stepping through my node points. And I'll just show, I have a paper where I jotted this down from Tina so we can compare. So I'm going to go from ground and I'm going to start stepping up. So this point basically should be ground plus the voltage dropped over this nominal 2200 ohm resistor. So Tina said that node voltage was about 3.56 volts. So we're measuring 3.552, which is reasonably close when you consider the fact that we do have some error in measurement of the meter. And if the meter were showing just 2 decimal places, it would be really close to rounding up. Wouldn't quite round up, but we also have a little bit lower voltage that we're measuring. Okay, the next node of interest is up at the top, where we'll be looking at the source voltage minus the voltage drop over the 976 ohm resistor. So I've only got one place left that I can access that, and putting in my measurement. And we'll show our multimeter. We'll try to show our multimeter get in focus. So we have 7.65 volts, and Tina said that would be 7.66. So again, we're pretty close. We could go look and recalculate this with a lower source voltage and then include our meter measurement error using the specs for the meter and see if those numbers were actually within spec. So we're going to go ahead and look at the nodes between the branches. So here we got to be a little bit more careful and look, and had we trimmed the resistor legs, this would be easier. But we've got node, one of the nodes, I can't remember the Tina label, but this is measuring the voltage drop over the terminal series resistor before ground, and then the nominal 2.7K. So this is between the 3900K and the 2700K. As you can see, we're measuring 5.222 volts. It's a little out of focus, but you should see it. Tina calculated 5.23. So again, we're pretty close. So we have one more node that we need to capture. And that is between these, the other parallel branch. I'm going to pause while I make sure I'm in the correct position on my proto board here. paused? Okay, I think we were not paused when we thought we were paused, and paused were otherwise inverse. We'll assume that we need to demo that last branch. We've confirmed the branch between the 3900K, the 2700K, it was 5.22. And now we're going to confirm the voltage node between the 2200K and the 5.6. And so basically, if you can see, we have one node where we have a measurement point here, and we have another node where we have a measurement point there. A little bit showing the angle of the measurement points. So those are holes where we are continuous in between, where we're connecting to resistors that I left open so that I could make a measurement. I believe this is the right one. So that was the last one. Recording. Okay, so again, 6.5 volts, and Tina measured 6.52. So again, we're measuring a little bit lower across the board at all of our nodes and at our source versus what Tina predicted. And I'm going to go ahead and disconnect the source so we don't continue to drain down our battery. What we would do at this point if we wanted to reconcile those is first we could go back to our Tina and we could change the source voltage, and then see how that impacted the node voltages. Then we could also go back to our meter spec and we could use the as measured values and apply whatever our percent and counts plus or minus was, and then see if these numbers fall, see what our plus or minus range is, and see if the Tina numbers fall within that. Given what those are for this meter, it's almost guaranteed they would. So in that sense, we could say that according to how accurately the meter can make its measurements, it would be indistinguishable from the Tina numbers. So that would be the last step, which I'm not showing, but if you wanted to completely reconcile them, you could show that the Tina calculations and the as measured were the same within the error of your meter, having already reconciled the actual source and the actual values of the resistors, which we did in Tina and in our calcs. So that is it for our calculate, simulate, build, measure, and evaluate. So they all came out the same within our predicted error, and we know what's going on in our circuit.